Okay, well, welcome everybody. So this is the final presentations for the RU program, this virtual summer.
So my name is Abdirisak. I am an electrical engineering major at Frostburg State University. I am also a minor at mathematics. Me and Eleazar, we are working on multiphase computational fluid particle dynamics. And our mentor was Dr. Kumar. We were also working with a postgrad student.
So what multiphase flow is basically the interaction between solids and any type of shape or any type of material that's immersed in any type of fluid as well. It can either be gas or liquid. And these multiphase flows are can be found in various different types of industrial processes, like FFC units, fluidized bed reactors, bubble columns, and other type of chemical refineries. And computational modeling is very important in this field because as scientists and engineers, we want to understand these dynamics of how fluids and particles interact with each other in these types of applications. So in the long run, hydrodynamics will help us to better design industrial units and processes, and also be a model to help us understand more natural phenomena like mudslides, avalanches, and of the sort.
In our simulations, we have used several softwares. We first use OpenFOAM, which is an open source software written in C++ that's used for computational fluid dynamics. We also use it ParaView for data analysis and visualization. In addition, we use SDF-IBM code, which is created by EPIC group at LSU. So SDF-IBM code is based on version 6 and it's written C++. And lastly, we use a Python script written by Dr. Kumar, which we use to generate graphs. Navier-Stokes equation is the backbone of our program. But before I talk about what Navier-Stokes equation is, let's make some assumptions. We assume first the fluid is Newtonian and incompressible. Newtonian fluid means viscosity remains constant, and incompressible means density means constant. So these two equations are nothing but universal laws of physics. Let me start with a smaller equation on the right hand side. So that equation is the conservation of mass, and the velocity is a factor quantity which has a component on the y, x, and z directions, and it tells any movement of the fluid. The nabla sign or the gradient sign is the divergence of vector field. So the divergence of vector field is the partial derivative of with respect to the component of y, x, and z. The partial derivative is 0, and that means mass is conserved. The other equation is Newton's second law of motion, which is force is equal to mass times acceleration. So we are dealing with a fluid. So in this case, mass, we replace to a fluid sign, which is rho, which is density sign, which is rho. And dv dt is the rate of change of velocity, which is the acceleration. On the right-hand side of that equation is the force, but there are two types of forces that act on the fluid. Internal forces due to interaction between the components, and external forces such as gravity. So the first term is pressure gradient, excuse me. It's a factor, and it says fluid flows in the direction of the largest change in pressure. The middle term is the gravity, and the last term is the kinematic viscosity of that fluid.
So one of the quantities we worked with that we were focused on this summer was Reynolds number. And what Reynolds number is basically a dimensionless number that helps predict pattern flows in many different flow situations. There are variations of this formula for Reynolds number, but the one you see on the screen here is the most common one. It's density of the fluid times velocity of the fluid, and the diameter of the pipe, or any other length scale of the cavity, all divided by the viscosity of the fluid. In our specific case, we just use the simple formula of density over viscosity of fluid, with density just being 1 as a constant. So just 1 over viscosity of fluid. So you can already see there's an inverse relationship when running these simulations and plugging in numbers in this formula. If you want to increase the Reynolds number, you would decrease the viscosity. Whereas if you want to decrease the Reynolds number, you would want to increase the viscosity of the fluid. So I explored multi-phase computational modeling in the vertical open flow. You can see on the left-hand screen that there's a picture of what the cavity looks like. So it's basically 3 sets of walls. The top and the bottom one are parallel, and the middle one is spouted out in a way to make a cone shape. And immersion in this cavity can be any type of solid, but in my case, it was just a circle of 5. It was a circle of 5 particles in a row and horizontal, and they're all 0.5 radius each. And I mainly focus on the cases of 1 and 2 degree motion. And what that means is for 1 degree motion, the 3 particles in the middle were able to translate in the x-axis. And in 2 degree of motion, the particles were able to not only translate in the x-axis, but also rotate in the z-axis as well. So basically, our main focus for me was to monitor position, other parameters, position, force, velocity, as we change the Reynolds number. So here are components of how we ran the simulations. You can see that there's a picture in the middle, a text file called a solid dictionary. And in this file, we basically were able to edit how many particles were in the simulation, what types, their movements, etc. So you can see on the top, there's motions, and we have types of motions in the particles. For example, a slide X, meaning that it can only translate in the X direction, left to right. We also have another motion called static, and then that motion, the particle is not able to move at all. And towards the bottom, you can see the creation of the solids themselves. So you can see that the shape name is circle and the movement is static. And you can also see the last 3 lines, their position, the starting position, their starting velocity, and their starting angle in the simulation. And that all corresponds to the picture on the left. So you can see the visual representation of the 5 particles in the open cavity. On the right, on the extreme right, you can see a text file called transport properties. And this text file mainly just changed the Reynolds number. And by changing the Reynolds number, we changed the nu, which is the viscosity of the fluid. So when gathering data in simulations and open vertical flow, we wanted to see how these quantities change as we increase the Reynolds number. One example is position. So here we have 4 graphs, with each graph increasing the Reynolds number. And it's graphing the second particle in a 1 degree of motion. So meaning a simulation where the 3 particles in the middle are able to translate in the x-axis, and the first and the last particle stay constant throughout. So you can see in the first 2 graphs, Reynolds number 10 and Reynolds number 50, both particles too just instantly go to the left and stay constant throughout the simulation. And Reynolds number 100, you can see that there's a little disturbance in the beginning for the first maybe 2 to 5 seconds, where the particle goes to the left, but then cuts to the right a little bit, and then goes back to the left, and it's constant throughout. For the last Reynolds number 200, there's a vast difference from the Reynolds numbers prior before. You can see that the particle 2 is unstable in a way where it's periodically moving between two positions, positions 0.297, 0.2975, and 0.3. So we wanted to compare those results from 1D motion to 2D motion as well. So we set up the same experiment, the same simulation, all the parameters are the same, except now all the particles are rotating, not only translating the x-axis, but also rotating in the z-axis as well. So again, this is 4 graphs of particle 2 with the Reynolds number increasing. So you can see that Reynolds number 10 is basically the same as Reynolds number 10 in 1D motion. It moves to the left and it's constant throughout. But then at Reynolds number 50, you can see that there's already a little disturbance in the beginning, in the first 5 to 10 seconds, I believe. Unlike Reynolds number 50 in 1D motion, where it was constant throughout simulation. And in Reynolds number 100, you can see there's a vast difference where there's disturbance from the beginning and all throughout the simulation. And this unstableness is not even periodic, but is chaotic in the sense where it's moving at different positions at different times. And of course, we have Reynolds number 200, which is periodically moving. It's very similar to the Reynolds 200 and 1D motion as well. So here's a visual representation of the simulations we ran. And so you can see the interaction between the fluid, the particles in the fluid. So as you can see, when the viscosity is high, that means the Reynolds number is low. So most particles are not able to move or translate as much. Hence why you can see on the left screen in Reynolds number 50, not that much current is forming. But as you decrease the velocity of when you decrease the viscosity, the viscosity of the fluid, hence increasing the Reynolds number, more particles are able to translate on the x-axis, and this will create more current fluid and fluid current in the simulation, in the cavity specifically. Within the 2D motion, we wanted to collect data of how the angular velocity is also changing as we increase the Reynolds number. So you can see here the three particles in the middle and their angular velocity at Reynolds number 50. You can see that they all have a common theme, that they all go to a steady state within 10 to 20 seconds of the simulation. If you compare that with Reynolds number 100, you can see the angular velocity for all 3 particles in the middle are chaotic, in the sense that they never go to a steady state, or at least within the 90-second time frame, they don't come to a steady state. So again, there is a relationship between the increase of Reynolds number and the unsteadiness of the particle, whether it's position, velocity, or any other parameter. So my mentor, he encouraged me to create more simulations where we arrange the particles in different positions, just to see how the visualizations work. So here we have a formation of 2 rows. We have 3 particles on the bottom and 2 on the top. And the 3 particles on the bottom, the middle particle is free to move in the x-axis and rotate on the z-axis. And the last 2 particles on the end are only able to rotate on the z-axis. And the top 2 particles are stable in the x and y, and they're able to rotate in the z-axis. So here's just a simulation of what it looks like. I also made a simulation where all 5 particles were in vertical to each other. Again, the 3 particles in the middle were able to translate not in the x-axis, but in the y-axis. And the last 2 particles were able to, were stable throughout. So again, this is what a visualization looks like of a vertical formation for OpenFlow. So, and each of the simulations I showed you, they were both at Reynolds number of 1,000. So there's a lot of current forming.
So this is the guy I was working on was lead-driven cavity. And if I try to give a brief introduction of what lead-driven cavity is a classical fluid dynamic problem for incompressible viscous flow. The motive behind the lead-driven cavity simulation is to solve the steady and steady solutions and find the velocity and pressure distribution inside the cavity. So in my case, I was working on a basic lead-driven cavity problem. The problem involves a square 2-dimensional space with 3 stationary boundaries and 1 that's moving with a known velocity to the x direction. So the fluid element in contact with the moving lead move at the same velocity as the lead. The right, left, and the bottom boundaries has a velocity of 0. So the moving lead sets the fluid into a circular motion. On the right-hand side, on the left-hand side of the slide is, it's hard to see it, but it's a part of a solid dictionary. The solid dictionary is like a case control file. It contains important information such as shape of the solid, density, gravity, degrees of motion of the solid, position of the solid particles, and many other useful parameters. In my case, all my simulation particles were free to move on the x-axis and the y-axis, and also they were free to move, not to move, but rotate. Let me correct that. They were free to rotate on the z-axis. So after I completed the simulation, I was able to generate many graphics using a Python script written by Dr. Kumar. For these graphics you see on the screen is position versus time of a case with a 500 Reynolds number and a solid density of 1.2. The particles were on the x-axis, and as can be observed from the graph, approximately at t equal to 50, the flow inside cavity is already or very close to a steady state. The common feature of those 4 graphs is a different 4 particles. For example, particle 1 is the lower left side, part 2 is the lower right side, and 2 and 3 are particle of 3 and 4. So they were in common, they were changing with time. This is another graph of a position versus time, but in this case, the particles were aligned on the horizontal axis, and the Reynolds numbers was again 500, but the solid density was slightly different, which was 1.05. There is not much of a change. The particles were about steady state around 50 when the time was 50, and yeah, that's very much the same. I was experimenting when I was changing the density. I was looking if I can see and visualize a big difference. If we change the density, can we see a difference? So in this case, there's not much of a difference. This is again a position versus time. of a case of a horizontal axis, the case has a Reynolds number of 1,000. Unlike the previous graphs, the solid particles are in a transient state most of the time, so it takes longer to reach steady state. So transient state, as you guys know, is it's changing with time constantly. But when I was graphing, I cut like a 60-second, and I observed that it was close to steady state. So yeah, next slide, Eleazar. Yeah, this is another graph of final position versus time. This time the particles were on the vertical axis. I didn't change the density because from the previous graph I noticed that density doesn't have a big effect on the movement and the position of the graphs. So I kept the density constant, and this is what I get. So from the last graph on the bottom is where I cut like first 50 second, and I was repeating itself, and that tells me, although it's a periodic, but it tells me it doesn't change that much, so it's a steady state. And this is the position of the y particles on the y-axis. So it's like the same, but it's inverted. So that was the x positions of the particles, where the positions were on the x-axis, and this is on the y-axis, and it's a consistent. So that tells me I was doing at least right thing. And here is one of the simulations I made. The fluid density is 1.05 and the Reynolds number is 1,000. So if we increase the Reynolds number, it decreases. If we increase the Reynolds number, it decreases the viscosity. And yeah, that's another case where the particles were aligned on the vertical axis, same density and same Reynolds number, and we observe the motion is very much the same. And that will go ahead.
So in conclusion, for my case, you can see that at low Reynolds numbers, the particles are steady and they remain constant at a longer time. But as you increase the Reynolds number at a higher state, more particles become be able to translate more and more stable, moving in the periodic or chaotic state, and thus creating more current flow within the cavity. And also, when it comes to 2 degrees of motion, particles become more unstable at earlier Reynolds number.
In addition to that, what I observe is the fluid inside the cavity in my case is incompressible, which leads the flow's Reynolds number being the dominant parameter. So if we change the density, it might change, but it's not noticeable. But if we change the Reynolds number, so increase or decrease, it changes a lot. And that explains the definition of Reynolds number, because it's the ratio of inertial forces and viscous forces. So that makes sense.
Yeah, so that's the end of our presentation. We just have to we want to give special thanks to Dr. Kumar. I don't know if he's here right now, but for just teaching us, the concepts of hydrodynamics. And not only us teaching us new concepts, but teaching us how to be like an excellent researcher in the field of academia. Yeah, I also want to thank our graduate student that we're working with, David, for just helping us, and me and Diria working through other stuff that we didn't know when Dr. Kumar wasn't there. So yeah, just give you very special thanks for this research experience.
Okay, thank you. Questions? Don't be shy. I have a question. Eleazar, in your course, it looks that you have beat. You know, you have, beats as in music.
The graphs, I think.
Yeah, the graph. You know, you have sinusoidal, but they were grouping. So these have
Angular velocity, I think, the Eleazar.
yeah, because you have two times
No, the other
there,
one.
no?
Yeah, that one, I think.
Yeah.
Is that what you're
Yeah,
talking
so-
about? Yeah.
Yes,
Can you say that again? I can't hear you.
you know, you have beat in music. If you plot the way
Oh, okay.
you said, you get this beat, you know, a similar pattern. So, and this is because you have two time constants, you know, in the when you play the music. So I wonder here, you may have something similar, no? You have two
I
constant.
didn't realize that. Thanks for the observation.
Yeah.
Yeah.
I mean, so I will be interested to know those two constants.
Right. Okay. Yeah. That's very interesting. I didn't notice that.
Yeah, I don't have a clue. So I mean, ask Kumar about that. Any other question? Okay, if there are no more questions, let's thank Eleazar and Abdil. Thank you.
Thank you, guys.
Thank you.
Okay, we are running a little late already, but I mean, sorry, we started late. So our next speaker is Ilia Hernandez. So wherever you are ready, you can share your screen.